SwayamPrabha. Digital India. Educated India.
Okay, good afternoon. My name is Ramesh Singh and I'm a professor in mechanical department and I work in a lab called Machine Tools Lab. So today what we'll do is we'll talk about what I do as research in a Machine Tools Lab, and there are a lot of products that have come out of my lab, and I'll actually take one product in particular, laser vent cleaning, and walk you through the entire development process of that product. So first thing is that we are all at IIT Bombay, and then I would just like to give you some details about IIT Bombay. We have 15 departments, 16 centers, four interdisciplinary programs, about 650 faculty members, a decent amount of R&D funding, 10,000 students, give or take, out of which 30% of our student body is PhD. So despite what we think that it's a UG-centric institution, we have a significantly high number of PhD students, and a few of them work in my lab, who are involved with these kind of product development and basic research which leads to product development. And then we have support staff and infrastructure which actually supports our research. And I am part of mechanical engineering department. Mechanical engineering department does a lot of things. Some of the key areas of research is something called micro nanotechnology, computational methods, fluid mechanics and thermal sciences, manufacturing. Then there is bioengineering. Basically that's the need of the hour because a lot of the products of future related to healthcare, and also to enhance our quality of life. And then solar power energy, because energy again is a big issue. So we want renewables, so solar energy and solar power is also one of the focus areas of research. So basic research area which I do in my lab is, first one is micro machining. So either I can subtract material, which will be machining. Machining are of different forms. I can do tool-based machining, I can do electrochemical machining, I can do electrical discharge machining, I can use different things to remove material. Or what I can do is I can add material, which we do in additive manufacturing, or I can do joining kind of a process where I can do weld multiple things and make a product out of it. Or I can do something like casting and forging, which is mass conservation process. We don't only develop the process, we also develop the machines to work with it. Because these machines are commercially, some of them are available, very few though, but they're very expensive. So I'm innovative and I actually go ahead and build those machines. And then once you build the machine, there are some challenges with the process itself. Because the tools which I use, just to give you some idea what tools I use in machining, can be 1/4 of your human hair, 20 microns. The second thing what I do is I call it something called flexible reconfigurable fiber laser manufacturing. The reason I use that is that I don't have money to buy 5 different machines. So what I do is I buy one laser and I basically make changes to the spot size, the powers. So basically I can do very high energy intensity to ablate the material, sometimes low to heat the material. So I can melt the material, I can heat the material, I can vaporize the material using the same laser by changing the optics. And a combination of other things to do certain things, so do like texturing, sometimes hardening, sometimes adding material and printing. So basically printing is nothing but you add powder and melt it and create layer by layer a structure. So that's what you do. So I actually do all those things with lasers. Then, since I teach mechanical engineering, I have to understand what is happening mechanics wise. Since I'm doing all these things these days, everybody's doing bio, right? So I said I cut steels, why don't I cut tissue? So a couple of students, what they do is they try to figure out that if I take a tool and poke a tissue, what will happen? Earlier days, people used to just do a big incision and do the surgery. Nowadays, you can come out of surgery in a day because they do a very small thing and then they would do something called laparoscopic surgery. They'll put a cannula and then they'll put a tool which would go ahead and do it local surgery. Now they're not seeing it, although they do have some cameras to look at it, but they don't have full vision now. A lot of it depends upon the feedback. So I'm cutting liver, I'm not cutting something around it, right? So they feel it. So a lot of it would be how the force response of a tissue is. So we want to study that and then get that idea to make some simulators or make some tools where people have a feel a priori before he does the first surgery. If he does 10 surgery, it's okay. But then how do you make sure that the guy goes and does the right things? Because bone feels different, liver feels different, stomach tissue will feel different. I have to go do liver surgery and I go cut my stomach. The only thing stopping me is stomach feels different. If I'm poking there, it feels different. Create more realistic surgical simulators. We only have managed to just get the forces from different models. So this haptic feedback would be based on this knowledge that what tissue gives what forces. So this information will build the backbone of it. Now these are some snapshots of the lab. We have a whole bunch of machines. Since the name is Machine Tools Lab, all we do is we have a lot of tools. We have excimer laser, wire electrical discharge machining. We have something called white light interferometer for surface toughness measurement. So if you machine something, you need to measure the roughness. That's the tool for that. There's a micro machining center, it's a commercial thing. And then measuring microscope. We have lots of surface roughness and metrology characteristics because what we make, right? I do micro machining. So I should be able to measure things which I do. So a lot of these equipments actually help me measure what I do. So I need to be able to measure few microns. If I'm making a channel of 100 microns, I should be able to measure it. This is called a coordinate measuring machine. So what it does is any shape you make, it can give you exact measurements of it. This is a very old machine which we have in our lab, but the newer ones can give you 3D models. You just put the product, they will take data all around it. They have a probe. They will go and get all the data, surface data, and build you a 3D model for it. A lot of my money, which I do in my research, comes from industry. And the industry typically, if I take money from industry, I have to give them something. So this is what would be probably of more interest to you being design students, that how do I go ahead? So they come with a problem, right? So then I have to interpret the problem in a way which makes sense to me, have a path to design it, have some engineering analysis to back it up, whether it will work or not, and then finally design and build it, and it should not be ugly looking. We designed India's first ultra high-speed micro machining center. That I told you that there are processes for forging, right? Where what you do is you heat the material and shape it using a forge, using a die or a mold, right? So what happens is after a while, since you're taking hot metal and usually compressing it, right? It can wear. So basically what will happen is it will not have the correct shape after that, right? And if it has cracked, eventually it can actually crack and break. So these things are fairly expensive. Each mold can cost you up to 30-40 lakh rupees, just one mold, right? And you can just throw it away. So we have developed a very high fidelity model, which actually takes into account if the material melts and resolidifies, there are changes in the microstructure. And these changes, what they do is they create volume dilation and transformation-induced plasticity. So, and there is thermomechanical contraction, because as the material cools, it will contract. And this contraction will not be even, because the higher temperature will contract more, the lower one will contract less. So there will be a differential contraction post-cooling. That will create stresses. And then there are transformations in the microstructure because you cool it very fast. All of them will have a role in the residual stress. For those of you know what residual stress is, it basically means the moment I cool and everything, there's no load, still there will be a stress in there, locked stresses. What it will do is if it's tensile, right, and there's a small crack, the tensile stress will open the crack. So your fatigue life gets compromised. So if I do it just by depositing, not knowing what kind of stresses are evolving, not understanding the process, I barely do a job which will fail again in 3 cycles. Do 3 more forgings and again it will fail. So if I understand the process mechanics, do it the scientific way, with the scientific knowledge, I'll probably be doing something which has a much longer life. So that's what I'm making a good case of, doing it scientifically. You can do it, but if you do it scientifically, it will be more sustainable. Whatever technology you are developing has to be enabled by science. Okay. Now, so what we propose to do in this is, if somebody comes to me and says that we have to develop a repair for that, you know what I'll do? I'll actually first create a automatic scanning system. It will go ahead and scan. compare it with the solid model, that what is the actual product look like, and then it will identify this is the defect, these are the defect areas. Then it will go ahead and take a powdered material and then do a local 3D printing there, local deposition of material there, and at the process parameters which will not create undesirable residual stresses. So those process parameters will come from science, and the technology is the actual product and the system paraphernalia that goes along with it. So that's what we propose, and we call it the autonomous damage detection system, the material deposition system, and the entire thing which will come into one package would be called restoration system.
The filling of deformities layer by layer, does that create some problems like from the actual material which is?
Yes, it will. So you need to know what it will do. Most of the material which I make by forging, it's actually, so properties are same everywhere. But if I do layer by layer, the property variation will be there. Okay. And then I built another machine for BARC. They need very high speed bearings, very, very high speed bearings. And these things have to run 15 years, non-stop. Okay. So it has to be very reliable. Now they want to change the material from something what they use right now to sapphire. If I have to machine sapphire, what will be the biggest challenge? Crack is a big problem because it's a brittle material, and you need something harder to cut because sapphire as it is very hard. So the problem was, whenever you machine, you will create some cracks, and the only thing you can use to machine is diamond. So either you buy a super duper expensive machine to do something like this, which there are very few in India. So we said that, okay, we'll do it cheap. I'll run it in my lab. I actually machined it in my lab with some cracks in it, little bit of cracks, minimum possible. I actually cut at 1 micron depth of cut, if you can imagine, pushed it to the limit. Still there were some cracks. To take care of that, we developed the polishing process. Now it's a very funny polishing process. I have a cavity to polish. How do you think I should polish this cavity if I have a cavity to polish? Of course, chemical is a good idea because then chemical dissolution would enhance the thing. But even to do that chemical dissolution evenly all the way through, I need to make sure that there is relative motion between all the points here. So the first thing that dawned onto me is do idli dosa thing. Make a ball that conforms to the thing and just moves. Now what will be the problem if I do something like this? The corners will rotate, the velocity will keep on going smaller and smaller and that center will stall. So there will be no polishing at the center. So what we did was, we did two things. One, we did it 45 degree. And then we rotated the ball also. So we did a double movement. So initially what we did was, we did something like this. We did a motion, a rotating ball with what they do in the idli dosa motion. That was a very kinematically very unsmart way of doing it. Then what we did was, we did this, and there's a very precise location. We started rotating the ball itself, the cavity itself. So now there is non-zero velocity everywhere, and build a machine like that. And of course, we use something that chemically reacts to the surface. So it's a combination of mechanical and chemical polishing, and gave the machine to BARC. One of the guys from CEAT Quality Control came to my lab and said that when they build these tires, right? So what happens is, there is misalignment between those edges. Once the misalignment is there, regardless of what we do, everything is a waste. Everything is a waste. And when they do the first pass of the tire building, there is a drum roll, and that tire, that basically the rubber piece is rolled over it. It is fed automatically and get rolled over automatically. Now what happens is, if the alignment is off, so they have two laser markers, and the guy eyeballs it. The requirement is 3 millimeters over 1.6 meters, and he eyeballs it like this. If it is not right, he will take it and do it again by hand. Each time he does it, he could have built 4 tires automatically. Each time he unwinds it, he is losing time for 4 tires of manufacturing. So they came up with a solution. They come and tell me, what we'll do is we'll take a scale and measure it. I said, how on earth you can measure 1.6 meters and get a 3 mm accuracy with 1 mm least count of it? How will you even see it? So one guy will see there, other guy will see there, and either is 1.5 and here there is 1.5 mm. I said, this is crazy. There's no going to work. Then he says, then what I'll do is I'll design a special caliper, exactly the same which I want, and put it there. I said, you'll use caliper on a rubber, on a compliant material? 3 mm will compress it. So every time your product will be right. Put a caliper, it will just compress, the material will compress. The compliant material, it's a rubber, right? I said, so I told them the only way to do it would be that you have a good vision system. Take a camera, measure it real time, measure it very fast, do it at various locations while the tire is rotating. Locate it as every location. So I said that every 10 degrees, get a data and then do it. So we actually built a system for them. Every 10 degrees it measures, it actually takes the laser mark, identifies the edge, measures everything, how much off it is, computes real time, and tells the operator it's good or bad, and logs the data to their quality system. So the entire system we designed and built for them. Now this went out fine. One of my old students who has a company now, designed everything. Now what happened was, they came to us and say that we have another problem. This is what I'll talk today primarily, the vent cleaning system. They came to my lab, oh, you use lasers. We have a problem. The problem what they defined was very simple. They said that we have these molds, right? So tires, they will take, so all this tread is actually molded. You take tire and you take a heated mold, get those shapes, cool it, take the tire out. Now what will happen is all these molds, any mold will always have vents because the material has some porosity. So the gases will come out. So the gas has to come out and these vents would be there. So these vents, what happens if I do it, say about 1,000 odd cycles of molding, these vents get clogged. And if I do more of it with the clogged vents, the quality will get compromised because my air will not escape. So there will be porosity in the product. You don't want that, right? So the way they clean it is, somebody actually takes a drill, 600 micron drill, and by hand, each tire has 1600 vents, 1600. Somebody goes and does it. Okay. You have seen a new tire, right? Each tire will have hair-like structure. That's called a spew, vent spew. So that hair-like structure is because you have vents. So you will actually, new tire you will see everywhere, even on the radial face, but on the side walls you see even in the old tire. If you look at the side wall, there these tires will, these spiky things will always be there, even in the older tires. Those are vent residues. So this is what actually goes into the vent, and that's what needs to be cleaned. So they will take a thing and tap, they'll clean it like that. But that's a process where it is inherently very dangerous. Tool can break. If the tool breaks, what will it do?
The broken part will be in the vent.
So it can be in the vent. That's also not required. And for those of you who have never done drilling, if a drill breaks in a hole while drilling, taking that thing off is a nightmare. Ek to hole gaya, and then the other thing would be that to take out is a bigger pain, right? So now that's one issue which is there. So what happened to them? The C8 guys actually gave a tire with metal embedded in it, and their entire batch was rejected by Renault. These guys come to my lab, you use lasers, can you do something? Can you design something which actually just removes all this drilling business? I said, why don't you send me the molds? Let me do some experiments. We'll use lasers to see whether we can clean these using lasers or not. So that's how this project evolved. Then a lot of these diamond guys come and work with me because they polish diamonds, but they never knew what they were producing. So they came to me and said that, I have an idea. I want to do digital personalization on jewelry and gemstones. So I said, what do you want me to do? So he said that, can you do some digital personalization? Every jewelry which somebody buys is unique. You can create an app where you can have a unique code on the jewelry. Somebody scans it. The moment you scan it, that unique code is linked with something on the web where you can have your love letters, pictures, messages, blah, 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 photographs pop up. So that will be a digital personalization of the jewelry. The jewelry will come along with a lot of things stored. It will have a unique optical code. So I said, I can actually make those codes. So what I'll do is I'll machine this small array of codes. Actually, these are just bunch of arrays of holes. Each array of holes, once it's scanned, it actually gives me a unique code. It's like a barcode or something. But since you cannot do it on jewelry, it will look cheap. I'll actually create a slightly fancier design, micro machine, of course with tools or lasers, and then you can do it. So the only problem with that would be that has to be amplified. So I'll give them a magnifying glass, a lens attachment with it. So anybody who buys the jewelry will get a lens attachment free with it, with the jewelry, which goes into your cell phone. So that will be additional tool which will be given to the guy who buys the jewelry, a magnifying lens. The ideas don't come in vacuum. You need solid science behind it to generate those ideas. So research is the driver for those things. Unless until I knew about lasers, I would not be able to make this machine. So I have some idea based on my scientific background that I can extend it to a product or extend it to a more marketable idea. Now every small component has been scaled down. So the scaling down can be in various fields. It can be in biomedical, defense applications, jewelry, electronics, molds for small features. So there is huge amount of scaling down of things. So traditionally, I don't know if you understand, people still used to make a lot of small things. People were making chips since 60s. So they were doing it. The only thing, the way you used to do it is, they will make a mask somehow, and then they would shine a laser on it or a UV lamp on it, and then they would etch it away. It's called lithography process. But then that will do only 2.5D, still used. All the chips are manufactured, the 7 nanometer technology which is there, the cutting edge technology uses lithography still. But they're primarily for silicon. And that's a process which you don't want to scale up. And it will not be used for every material. So what I say is, there is a nanoscale manufacturing which is good. We have the technology for it. Great. I have a macro world where all my machines are there. There is, in between, there is a micro scale where either I have to come from top or take these processes up there. That's a gap. All those lithography processes evolved for silicon. So if I have to use titanium, steel, all these metals, it's not easy to do. So why don't I take the macro scale processes, scale it down? So processes can be milling, drilling, turning, EDM. Now what is the primary problem? The primary problem is we don't understand the science also at that level. As I told you one example, right? What stiffness does. Right? The stiffness scales non-linearly. So we have to design a process in such a way the forces are very, very low. Any small force will break the tool. So fundamentally what we said is, the way to counter that would be that you go at 100,000 RPM. Normal machines run at 3,000 RPM. The problem at going at very high speeds is, for those who don't understand dynamics, certain frequencies can be excited. Any misalignment, if there is even atom of misalignment, it will be amplified, omega square r, if you remember that. So there will be alignment amplifications, misalignment amplifications. There will be some of the natural frequencies will be excited. And any small vibration with a very low flexibility, low stiffness tool is very dangerous. Tool will break. So you have to understand the science of dynamics very, very well in the machining process to be able to make it properly. That's a big challenge. So I can make a machine, but to operate the machine, I need to understand the process very well.